All right, welcome back. So last time we talked about first law of thermodynamics. Now we'll continue today. Um, so we talk about the thermodynamic system. So any system of your interest is called a thermodynamic system, and you can again categorize it as a closed system or open system. So closed system is it's not contact with anything else. So typically that doesn't exist. So everything is a closed, open system. Okay. We talk about the how to calculate work by a gas system. So you do integration of PdV that gives you the work done by the gas. Okay. And we talk about internal energy of a gas system for monatomic ideal gas. So you only consider the kinetic energy of the system. So it's 3/2 of kBT for individual molecular for the whole individual whole gas as a system. Then it's M times Na times 3/2 of kBT, which turns out to be 3/2 of nRT. Okay, for the internal energy for the monatomic gas. And then we also talk about Zeo's law to start with. So if A and B are having the same temperature and B and C having the same temperature, so then A and C should be having the same temperature. Okay, so the Zeo's law. We talk about first law basically says the internal energy change of the system equals to the heat change minus the work done by the system. Okay, derivative form differentiation form will be derivative of E internal equal to derivative of Q minus derivative of W. Okay. Convention for signs of the terms here, Q is positive when heat added to the system, Q is negative when heat is removed from the system. Work is positive for work done by the system, work is negative for work done onto the system. And a few thermodynamic processes we went one by one. So the first one, isobaric, the first one being isobaric, the second one being isochloric, and then isothermal, adiabatic, those four processes. If the system returns to its initial states, that means PV and T are all the same, then it's called a cyclic process. Okay, so in that case, because it returns to initial status, so everything returns to its initial status, so delta E will be equal to 0. Internal energy should be equal to 0. However, it could do work, okay? And during the process, there will be heat added in or removed, and work will be done by the system or done onto the system. So either way. So Q equal to W because delta E internal equal to Q minus W, where delta E equal to 0, that means Q that equals to W. All right. So heat capacity for gas systems. So we defined that heat capacity earlier using MC delta T. Okay, so then heat capacity is equal to Q over M delta T. Now, we didn't distinguish between different processes for the solid and liquid. That's because the volume change of solid and liquid actually is going to be small. Okay. Now, compared to gas, when you heat gas, gas can expand dramatically. So in that sense, we want to distinguish between a couple of processes here. So one is called the constant volume process. The other one is called the constant pressure process. So we'll take a look on the first one here. Constant volume process. When you use that, then the C from the definition of the heat capacity, we use C sub V. So that denotes constant volume. So Q then equal to mCV delta T. N is the moles of molecular. So we'll be using moles of moleculars instead of using mass, because moles will be the more popular term to use to describe the number of the gas. So NCV delta T. And you can actually go from moles to the masses by just doing moles times molecular weight, right? To all molecular mass, however you want to call, to get to the mass of the whole system. So in that sense, CV is equal to 1 over m Q over delta T, okay, with the V being constant. Now, if you have m moles of the ideal gas, because its internal energy is only determined by the temperature, right? Because we do not have potential energy involved. So E internal is equal to 3/2 of nRT. And if the volume is not changing, so delta V is equal to 0. So then the volume does not change, right? So then the work done by the gas will be 0 because it doesn't expand or shrink, okay? So in that sense, minus W equal to 0. So delta EQ then just equal to Q, or delta E internal just equal to Q. And so you have Q, right, equal to N CV delta T in the previous slide. So let's quickly go back. So Q equal to N CV delta T, right? So C NCV delta T equal to internal energy, which is 3/2 of nRT. So you guys can write this down and you can easily derive it, right? So delta E internal then will be 3/2 of nR delta T, right? Equals the Q, which is N CV delta T. So N and CV will cancel. So then the N CV will be just equal to 3/2 of R, okay? And again, this is related to the 3 degree of freedom for the kinetic energy going from X direction, Y direction, and Z direction. Okay, so that you get 3/2 or 3/2 of kBT in that sense. All right. So this is for ideal monatomic gas. So we define degree of freedom depends on possible motions of a molecule can have in particular dimensions. So just consider kinetic energy being the translational kinetic energy. So then you have 3 degrees of freedom, D equal to 3. Okay, so this method is called equal partition theory. Okay, where it depends on how many degrees of freedom, then you have the energy as each partition, in each direction degree of freedom will contribute 1/2 of K BT of energy to each molecule. Okay. Now for diatomic gas, in addition to the 3 translational degree of freedom you can get from X, Y, Z direction, you actually have 2 more rotational degree of freedom. So you can rotate in this horizontal plane, you can rotate in the vertical plane as well. Okay. So then in that case, the degree of freedom is 5. So your internal energy should be equal to 5/2 of nRT. Okay, which use that you can calculate the C sub V for constant volume should be 5/2 of R. Okay. And experimentally, this has been verified. So for monatomic gases, argon, helium, neon, they are 1.5, which is 3/2. For diatomic gases, carbon monoxide, hydrogen, nitrogen, oxygen, they are pretty much 2.5 or 5/2. Okay. And then F2 as well is close to that. Now for higher or polyatomics, it's going to be, so for 3 of them, you're going to have about 2 more freedom degree of freedom, so 7/2, so 3.5, close to 3.5, a little bit over 3.5 in that sense. Okay, let's take a look on this example here. Okay, so this one says professional divers has, so it says professional divers sometimes use heliox, which consists of 79% of helium and 21% of oxygen by mole. So that's like the count of molecules. Okay. Suppose now the reason of using helium instead of nitrogen is helium is much lighter than nitrogen. So helium is lighter. Okay. Suppose a perfectly rigid scuba tank with a volume of 11 liters contains heliox at an absolute pressure of 2.1 times 10 to the 7 Pascal at temperature of 31 degrees Celsius. The diver goes down to a point where the sea temperature is 27 degrees Celsius while using a negligible amount of mixture. As the gas in the tank reaches this new temperature, how much heat is removed from it? Okay, so let's take a look on the paper I have here and then see what we know about this problem and what we don't know about it. Okay, so what we are looking for. So there's helium. and there's oxygen. So helium is monatomic, right? So this is monatomic. This is diatomic for oxygen. 79% helium, 21% oxygen by volume. So the volume of the whole tank is 11 liters, which is, you can convert it into meters cube of the SI unit first. The absolute value, P equal to 2.1 times 10 to the 7 Pascal, okay? Initial temperature, so let's call it maybe T1. You can say T initial as and T final, that's no problem. Convert it into Kelvin, so you add 273.15, that would be 304.15 Kelvin. Final temperature, I'm going to call it to T2, 27 degrees, so that's 300.15 Kelvin. All right, so it's asking the heat, how much heat is removed. So you're looking for Q, all right? Q is equal to, now you have two mixtures, it's equal to M. The volume does not change, right? So NCV, or it can, I think they are both CV, so you can just say C1. So N1, C1, delta T. So delta T will be the same, right? For helium and oxygen, okay? So you just can just say T. N plus N2, so you can call this helium, 1 as helium, 2 as oxygen, and delta T, okay? So I think we have delta T. So delta T is T2 minus T1. So you can do T2 minus T1 minus 4 degrees Celsius, okay? Excuse me. And N1, N2, we don't know N1, N2, but I think we can calculate if we know the total number of the M, right? So if we know N total is equal to N1 plus N2. And they are having 79% and 21% respectively. So this one will be 79% of total. This one will be 21% of the total. All right, can we calculate total then? So to do that, we might want to use PV equal to nRT, right? So P is given, V is given. So P, V, and T should be referring to initial. Okay, so we'll use initial. So in that case, all right. So I think we have this strategy here. We calculate the total M, and then we can calculate N1, N2, and then we can put N1, N2 there. Now C1 and C2, we should be also able to find C1 and C2 because it gives us that the helium and oxygen, right? So they are monatomic gas and diatomic gas. So for C1, it's gonna to be length C1. So let me find a place. C1 is going to be equal to 3/2 of R. R is 8.31. C2 is 5/2 of R. Okay, so this is monatomic gas. This is diatomic gas. All right, so let's calculate N total. From here, it tells you N is equal to PV equal to RT. Okay, so M subtotal equals to PV over RT1 specifically. So this is 2.1 10 to the 7 Pascal times volume 11 liters. Okay, so 10 to the minus 3 over R1 8.31 joules over moles, and in Kelvin, and delta T will be minus 4, or in this case, no, not delta, sorry. It should be T1 will be 304.15 Kelvin. Okay, so use that. You find out the total moles to be 91.4 moles, okay, are moleculars. So of which 79% is N1. So 91.4 moles. That gives you 72.2 moles, right? And 21% of it is oxygen. So that gives you 19.2 moles of oxygen. All right. So then the heat being removed from the tank, okay, Q equal to N1C1 delta T plus N2C2 delta T. Okay, so the same delta T, so you can say N1C1 plus N2C2 both times delta T. All right, so N1 is 72.2 moles times 3/2 8.31 joules over moles Kelvin plus, okay, so we're going to use a square parenthesis there, 19.2. I'm going to just skip the units form right now. 5/2 times 8.31 because you should have everything else, everything in just SI unit, okay? Minus 4 degrees, okay? Kelvin, degree Celsius or Kelvin, so whatever, they are the same. Then we're going to just use Kelvin. Okay, so that turns out Q to be equal to minus 52.15 joules, okay? So this is the amount of the heat being removed because minus, so that means removed, okay, from the tank. All right, okay. So let's go back to the lecture slide, okay, and now move on. So now let's take a look at detail about the heat capacities of ideal gas. So we, in just the slides before, we have taken a look at the heat capacity for the constant volume process, right? Now you probably remember I mentioned the constant pressure process as well. So if we have constant process, then we call heat capacity as C sub B sub P, okay? From the internal energy change, which is Q minus W, as well as the definition for heat capacity. In this case, I'm using just a capital C. That means N times C. So small c will be molar heat capacity in that sense, okay? And this is just to use to compare the two heat capacity for constant volume process and the constant pressure process, okay? So based on that, C should be equal to delta E plus W, right? And then over delta T, because this W goes to the other side, becomes delta E internal plus W. So divided by delta T, that gives you the capacity, heat capacity, okay? So for constant pressures process, you have this delta E int internal plus W and then over delta T. So for constant pressure process, W is equal to P times delta V. Okay, now for constant volume, again, CV now equal to delta E in internal plus W over delta T. But for constant volume, because volume does not change, so delta V is equal to 0. So this term vanished. Okay, so then you only have delta internal energy over dt. So compare the two, you will see that this guy has one additional term PdV on the top. So then Cp will be greater than Cv in general. Okay, again, for solid and liquid, the difference is negligible for the volume change. So we do not distinguish between constant volume or constant pressure process. Okay, so either way, the volume is going to be negligible. Volume change is negligible. All right, so now let's take a look on the C sub P in relationship with CV. So the conclusion is Cp is equal to Cv plus Nr. So now just make a note here, when I have the Cp and Cvs here on this slide, they are specifically for molar heat capacity. So that means it's heat capacity per mole, okay? So Cp dt equal to d internal plus q d p dv. So this is dq, okay? And then this is derivative of internal energy plus this is the derivative of work. Basically, so this is using the differential form of the first law of thermodynamics, which says derivative of E equal to derivative of Q minus derivative of W, okay? For a constant volume process, you have this term. For constant pressure process, you have PdV on the right-hand side. For constant volume, PdV goes to 0 because constant volume means dV equal to 0, okay? So then this Cp dt then is equal to dE internal. So this then can go there. So Cp dt equal to Cv dt plus Pw, okay, in this case, expression. And you can divide everything by derivative of t, right? So then get rid of this guy, get rid of this guy. So then this will be plus P times dV over dt, okay? Now for ideal gas, let's evaluate this term. So PV equal to nRT, right? So you can do derivative on this side, which is equal to derivative on the other side, right? So dPV will be equal to VdP plus PdV, okay? That equals nRdt, okay? So then you can see, now you divide everything by dt, okay? So dt goes here, dt goes there. So then VdP over dt, okay, plus PdV over dt is equal to nR, okay? So in this case, then you can see, if we are talking about constant pressures process, right? So C of P, then it should be equal to Cv plus, which this one, PdV over dt. So PdV over dt should be equal to nR because for constant pressures process, dP goes to 0. So this guy goes to 0, okay? So dP goes to 0, so then you have that. So P dV over dt then equals to nR. So Cp equal to Cv plus nR, okay? Or wait a second, I'm sorry. In this case, this is still just heat capacity for whatever moles of the gas you have, okay? So again, this is capital, 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 okay? So in that sense, then Cp sub P equal to Cv plus nR, okay? So then talk about just this molar specific heat capacity. So then capital Cp over N equal to capital Cv over N plus R, okay? So in that sense. Okay, so then in this figure here, or in this table here, should be considered as molar heat capacity. So it's the heat capacity for the collection of gas divided by the moles of it, okay? So so then we don't have N. So for ideal monatomic gas, C sub V is 3/2 of RT, okay? But C sub P is this guy plus R, which gives you 5/2. Diatomic, 5/2 of R, and then plus R gives you 7/2 of R, okay? For polyatomic, so when you have 4 or more atoms in that sense, okay? So then you will use those numbers, okay? So again, for monatomic ideal gas, internal energy is only from the translational kinetic energy. So INT equals to 3/2 of nRT. Therefore, CV equal to 3/2 of nR. Cp equal to Cv plus nR equals to 5/2 of nR. So then for just molar heat capacity, that means Cv per mole. So then divided by N, okay? And then this will be divided by N. So 3/2 of R or 5/2 of R. All right. So example again. So this one says the heat capacity at constant volume of a certain amount of a monatomic gas is 49.8 joules per Kelvin. So it says heat capacity. Okay, so we want to be careful, not molar heat capacity. So this is the total heat capacity. That means the molar heat capacity multiplied the numbers of moles you have. So you can use that to find the number of moles, right? For monatomic gas, let me stop sharing and then switch to the paper to show you guys the work on this one. All right. So monatomic gas, CV equals to capital C, okay? Heat capacity equal to actually is 3/2 of NR. And it tells you that's 49.8 joules over Kelvin. So use that, and then it's equal to 49.8 joules over Kelvin divided by 3/2 times, right, times R, 8.31 joules over Kelvin times mole. So then the result will be in moles. So you then can calculate this is about 4 moles. Okay, 4 moles of gas there. What's the heat capacity at constant pressure of this gas? So we are looking for C of P. So again, not molar, so capital C. Then should be equal to 5/2 of NR. Okay, so 5/2, 8.31, and then 4 moles. Okay, so I'm using everything in SI units, so I don't have the units there, but this is about 83. Okay, 83 joules over Kelvin for this one. It's asking what's the internal energy of the gas at 300 K. So internal energy of the gas, this is monatomic. So 3/2 of RT of nRT, okay? And 3/2 of nR is that guy. So you can do that guy times T. So 49.8 joules over Kelvin times 300 Kelvin. Okay, so once you are clear with all the quantities, this guy looks like a little bit straightforward problem. So 14,400 or 940 joules, okay, of energy is there. All right. Now going back to the problem, switch camera. So we'll be moving on and look at the adiabatic processes for an ideal gas, okay? So again, this is ideal gas. So whenever you see ideal gas, you realize you can apply PV equal to nRT, okay? And then for adiabatic process, so adiabatic process says that should be dQ equal to 0, okay? Now, we'll start with monatomic gas. The internal energy consists of translational kinetic energy only, so internal energy equals to 3/2 of nRT. So then C sub V will be equal to 3/2 of nR. Okay, starting from the, again, first law of thermodynamics, this is in differential form. So derivative internal energy equal to dQ minus dW, dQ being 0, okay, for adiabatic process. Adiabatic process is a process that have no heat transfer. So dQ equal to 0. So the internal energy, okay, is then equal to minus of dW, which is minus d of V. Now, the internal energy is equal to, in this case, derivative internal energy, right? So equals to 3/2 of nRT. This is 3/2 of nR is C sub V, so C sub V of dt there in that sense. And that's equal to nRT divided by V times dV, okay? Because this is from PV equal to nRT, P equal to nRT over V, okay? So CV dt equal to minus nRT over V times dV. So we can move this guy to the other side equation. So and then just doing a little bit of the rearranging our terms. Okay, divide both sides by CV first, or actually we rearrange divide both sides by CV first, and then divide both sides by T. Okay, so then you have dt over T. You on this side you have nR over CV times V dV. Then move this guy to the other side. Negative becomes positive. So dt over T plus nR over CV dV over V equal to 0. You can do integration, right? So integration of this guy gives you natural logarithm, okay? And then integration of this one gives you also natural logarithm. Integration of the other side gives you constant because it's 0. So this plus this guy equal to 0, that means you can actually, so this constant before the natural logarithm actually goes into the natural logarithm, becomes the power of this term inside, right? So it's natural logarithm of v to the power of nr over cv. So v to the power of nr cv. And ln function add up to be ln of a plus ln of b. It becomes ln of a times b. Okay, so a times b. So basically ln of t times n times v to the nr over cv, okay, equal to constant. And then you do exponential function to both sides of the equation to get rid of ln from the left-hand side, okay? So exponential or constant should be also constant. So again, you're writing as a constant, but this now becomes t times v nr over cv, okay? Now, if you remember, we got Cp equal to Cv plus Nr. So then Nr is basically Cp minus Cv. Okay, so in that sense. So then Nr equal to Cp minus Cv. So this guy then becomes Cp minus Cv over Nr. And that becomes Cp over Cv minus 1. We call Cp over Cv gamma. So then it's gamma minus 1. Okay, so this to the power, v to the power of this guy becomes gamma to the 1. So then you can say tv to the gamma minus 1 equal to constant. Or you can do tv to the gamma, and minus 1 is v to the minus 1, right? Divided by v equal to constant. So either this one, expression of this guy, or this guy, they are both expressions for the adiabatic process. Now, let's take a look on the ideal gas PV equal to nRT again. So T divided by V from here, T divided by V, you'll see then is PNR. Okay, so P over constant. Okay, so P over V is P divided by a constant. So then you can say P times V to the gamma power is a constant. Okay, where gamma is equal to Cp over Cv. All right, so this is the adiabatic process. In addition to PV equal to nRT, then you have a second equation for adiabatic process. PV to the gamma equal to constant, where gamma is Cp over Cv, and Cp is always bigger than Cv, so gamma is a number that is bigger than 1. For monatomic gas, Cp will be 5 halves of Nr, Cv will be 3 halves of Nr, so gamma will be equal to 5 over 3, okay? Oh, yeah, so gamma will be equal to 5 over 3 for monatomic gas. For diatomic gas, because C sub V is 5 halves of Nr, C sub P is 7 halves of Nr, so then gamma will be equal to 7 over 5, okay? All right. The work done during the adiabatic process, you can calculate it, okay? So this start with, again, the differential form of the first law of thermodynamics and dq being 0. So then d of internal energy equal to minus d of w. And internal energy being 3 halves of nRT. So then d internal energy should be 3 halves of nR dt. 3 halves of nR dt, okay, equal to minus of dw. So dw equal to minus of 3 halves of nRT, which 3 halves of nR is Cv for monatomic gas. So minus Cv dt, okay. So then you can calculate, you can do an integration, all right, of dw to get w. So minus Cv, and if dt is not a function of temperature, or if Cv is a constant, so Cv is not a function of temperature. So then integration of this side equal to integration of this other side. So minus Cv of T final minus T initial. So that would be your W. Or you can write Tf as, so this is starting from PV equal to nRT. So PF VF equal to nRTF. So then TF equal to PF VF over nR. Ti will be Pi Vi over nR. Okay, so you got that. So then Cv over nR, okay, minus CV over NI, and then PF minus PF VF minus PI NI. There you go. CV over NR, if we go one slice back, we have NR over CV, which means CP minus CV over CV, okay, which is gamma minus 1. So then this is equal to minus PF VF minus PI VI over gamma minus 1, okay? So I think there's a lot of derivations here, so you want to follow it closely, okay? W equal to, at the end, this guy. So this could be one of the expression as well, all right? Let's take a look on the example here. So this one says 0.50 moles monatomic gas, okay? At 400 K and kPa and 300 K Kelvin, expand quasi-statically until the pressure decreases to 160 Kelvin, kilopascal. Find the temperature and volume of the gas, the work done by the gas, and the heat absorbed by the gas if expansion is adiabatic. Okay, so for adiabatic, now a few key things here. So one thing, so whenever you see again ideal gas, you will just put down the ideal gas equation PV equal to nRT first. That's the equation you can refer to or you can use it, okay? So ideal gas, that means PV equal to nRT. Monatomic gas, so that means C sub V is equal to 3/2 of nR, okay, or monatomic. M in here is 0.500 mole. And P is equal to 400 kilopascal times 10 to the third, okay? And temperature equal to 300 Kelvin. So let's call this P1 and T1. And it expand to P2 equal to 160 K. Okay. And if it wants you to find what will be now the volume or temperature and volume, what will be the volume, temperature, okay, and work done by the gas, and the heat absorbed. Okay, so four quantities. If this is an adiabatic process, so now adiabatic, that means you can do P, right? For adiabatic process. So PV to the gamma, okay, PV to the gamma power equal to constant. So that's one of the expression, okay? All right. Now, for the gas system, again, the first law of thermodynamics should also apply, okay? So just keep in mind delta U equal to, or delta E, internal equal to Q minus W, okay? So let's take a look on here. So you can calculate volume final, right? So gamma is equal to actually, so gamma equal to Cp over Cv. So Cv being 3/2 of that, so Cp then will be 5/2 because Cp is Cv plus Nr, so 5/2 of Nr over 3/2 of Nr. Okay, so that means 5 over 3 for your gamma. So PV to 5 over 3 power is equal to constant. That means P1 V1 to the gamma is equal to P2 V2 to the gamma. Okay, so by using this equation, you should be able to calculate the let's see, V2. Okay, for V2 quickly, because you can calculate V1. This is N PT. Okay, so using PV equal to nRT, you should be able to calculate V. Okay, and then once you have V2, you can calculate the T2, right? And you can also calculate work. Okay, and then see how much work will be done. So let's do this one by one. So that's fine. P2, actually we are finding V1 first. Okay, so P1 V1 equal to N T1. So then V1 equals nRT1 over P1. So 0.5 moles times 8.31 joules over moles times Kelvin times T1 300K divided by 400 kilopascal. Okay. So that's your V1. So your V1 is 3.116 times 10 to the minus 3. Okay. Now P1, so use this equation now. P1 400 times 10 to the third Pascal times 3.116 times 10 to the minus 3 meters cubed to the 5 over 3 equals to P2 160 kilopascal. So kilopascal times V2 to the power of 5 over 3. Okay, so you rearrange the terms and then so divide both sides by this guy, and then you do square root of now to find V2 square root of everything. So 1.6 times 10 to the third, 1.6 times 10 to the third. Okay, and then square root of, to get this, you do square root of 3 over 5. Okay, for V2. So it will tell you your V2 is equal about 5.40 times 10 to the minus 3 meters cubed, which is 5.40 liters. Okay, so let's just do that, the SI unit, okay, for the V2. All right, now once you have V2, you can find your temperature, right? Your temperature T2. So you'll use PV equal to nRT. So again, just back and forth with these two equations, you can find most of the quantities you are looking for. So P2 V2 equal to nR and T2. So T2 then equal to P2 V2 over nR. So P2 1.6, 10 to the third, V2 5.4, 10 to the minus third, over 0.5 of moles, and then 8.31, actually joules over moles and Kelvin. Okay, so it turns out to be 208 Kelvin for your T2. Okay, so we have this one, we have this one now. We are looking for work done and the Q. So for work done, if you know the equation to use, it's going to be P final, V final, right? Minus P initial, V initial. And that should be, and then divided by gamma minus 1. Okay, so you can go up a couple of slides back and then find the equation to use. But this will be minus, okay, in the front. All right. So this is equal to minus of, you plug in the numbers, your numbers, 160 times 10 to the third Pascal, V2 being 5.40 times 10 to the minus 3 meters cubed, and minus 400 times 10 to the third Pascal, and initial volume of 3.116 10 to the minus 3 meters to the cube, okay, divided by gamma minus 1, gamma is 5 over 3 minus 1. Okay, so at the end, you get work equal to 574 joules. Okay, so that's the expansion of work. All right, and at the end, you're looking for what will be the heat absorbed by the gas if the expansion is adiabatic. So 0, right? Adiabatic, that means 0. So no calculation needed for that part. Okay, let me show you the full work on this problem. All right. So we'll stop here for today, and we'll come back on the next lecture. Okay, so see you guys. Bye.